Hi class, welcome back. Again, we're going to continue our look at the differential forms of Maxwell's equations. So today we do the final one, which is Gauss's law for magnetic fields. Thought for the day comes from Matthew 15:10 through 11. And it states there, "And he called the people to him and said to them, Hear and understand, it is not what goes into the mouth that defiles a person, but what comes out of the mouth. This defiles a person." So I always think about this verse, or when I read this verse, I think about Maxwell's equations, especially Gauss's, when it talks about, the fields that are going to be penetrating a certain enclosed surface. Of course, on the electric side, if there's charge inside of the surface, then it's going to create that displacement field, right? And so it's not what's outside going in, it's what's inside the surface coming out, that charge coming out. And so I think that's the same thing, a similar concept here is what Jesus is saying is, it's not really, the substance isn't created by what goes in, what comes out is created by the substance that's already inside of us. And so I think that's a pretty clear indicator. And so hopefully on occasion you do stop and take inventory, about what's coming out of your mouth, and that, that does give us some indication of what's in our heart, and that, we would deal with that. So anyway, I thought that was kind of an interesting correlation there, and kind of went together. So we're getting close to being done with part 3. We'll do Gauss's law again for magnetic fields this time, and then the next lecture we're going to look at divergence and the divergence theorem, and that'll wrap up this section. So let's dive in. Gauss's law for magnetic fields and differential form. So we can take a look at this. We can recall from our earlier lectures that Gauss's law in integral form is stated this way, and this simply states that if we sum the magnetic field normal to an entire enclosed surface, that total magnetic field's got to equal to 0. And again, this is where this S is a closed surface, and so it's creating a volume from that surface because it is enclosed. So we want to do the same thing again. So we're looking again at a 3D box with sides x delta x, y delta y, and z delta z in length. We're going to consider this general magnetic field. So it has x, y, and z components, and each of the components can be dependent on x, y, z, and t, so their position and time. And then again, just as we did before, the box, just to get a visual, it has a delta x, delta y, and delta z, and it starts at some point x, so then this point would be x plus delta x. That's where we get that, get these terms here. So the magnetic flux emanating from this box can be broken down into 6 separate equations because there's 6 sides and we can handle them each separately. So if we look at the surface of x equals x, we'll have an x component, and that surface is defined by delta y, delta z in length. So it's this component evaluated at x going through this surface. Likewise, at x delta x, we evaluate our magnetic field at x plus delta x, and the surface that we're looking at that it'll be normal to is the delta y, delta z again, same surface. We can go now on the y directions. There's 2 surfaces, one at y and one at y plus delta y. So the one at y, we evaluate the magnetic field at y, and then the other 2 components are what are going to form the surface that we're dealing with. So it's delta z, delta x. Again, for y plus delta y, it's the same surface area. This time we're evaluating the magnetic field at y plus delta y. And finally, for the z surfaces, for z equals z, we got delta x, delta y, defining our surface and magnetic field at z. And finally, at z plus delta z, same thing, delta y, delta x, and then we're evaluating at z plus delta z. So now we can combine these terms, and we can now come up with an expression for the total magnetic flux emanating from this box as follows. So we pull out some like terms. So we know for all six, we can do them up in 3 sets of pairs because we have 2 delta y delta z's, 2 delta z delta x's, and 2 delta x delta y's. It's just the difference in evaluating the field at those 2 points. If we now substitute these expressions back into Gauss's law for magnetic fields, you can see we'll end up having this equation here. We can rearrange this though by dividing through by delta x, delta y, delta z. So as we divide each term, you'll see we'll have the x components with x, the y components with y, and z components with z. So we can now allow the dimensions of the box to shrink to 0, just as we did before. So as we take this limit, so this will be the limit as x goes to 0, as y goes to 0, and z goes to 0. So hopefully we're getting used to seeing this now and recognizing this term from calculus. This is the basic definition of a derivative. So now we can define these derivatives as the partial of x with the partial of the x component of b with respect to x, the y component of b with respect to y, and the z component of b with respect to z. And Gauss's law says these should all equal to 0. So we can rewrite this equation as we did before. Here, this is the same thing. If we dot these two together, we'll come up with the equation we had previously, because the x components, the y component, and the z components will be paired together. And hopefully we're starting to get the hang of seeing why we're doing these groupings. Of course, this grouping should look familiar. And again, this grouping here should look familiar. And of course, this is just the general expression for the magnetic field, our flux density. So we could substitute that back in. And as we demonstrated last lecture, this is what we're now calling our del operator. It's just a mathematical mechanism for taking the derivatives in each direction. So if we make use of this del operator, we can now define Gauss's law in differential form as del dot b equal to 0. Now, this del dot b, again, has a special term, it's divergence. So we'll say the divergence of the magnetic flux density has always got to equal to 0 over a closed surface. So this is Gauss's law for M fields, or magnetic fields. Let's look at one quick example. If we're given a vector, a general vector A, which is just y in the x component minus x in the y direction, y in the x direction minus x in the y direction. What we want to know is, can this represent a magnetic field? Well, we know from Gauss's law, if we take the divergence of this vector, it must always equal to 0. So if that's true, then this could be a valid equation for a magnetic field. So we can take a quick check of this. We do del dot A, or again taking the divergence. And so this would result in taking the derivative with respect to x of the x component and with y on the y component. Well, the derivative of y with respect to x is 0, and the derivative of negative x with respect to y is 0. So yes, this will always be 0. This divergence will always equal to 0. So since this is equal to 0 for all possible cases, this vector could be a valid representation for a magnetic field. If this was anything other than 0, it would not be a valid equation for a magnetic field.